Hello and welcome to my YouTube channel. In today's video, we are going to talk about simulation of Arduino using Proteus, and in this series today we are going to talk about the use of ADC or analog to digital converter for analog read purpose. So let's start the video. So how the microcontroller can perform any analog read? To perform the analog read function, microcontrollers use a peripheral called ADC or analog to digital converter. Now the question is, what is analog signal? Analog signals are signals which are provided by the nature. So all the signals that we receive from the nature, such as light, temperature, heat, sound, flow of water, current, everything. Okay, so whatever is provided by the nature are all analogous, and all those signals are analogous in nature. Now, these analog signals are received by the ADC and they are then converted to digital signals. Okay, and for that we use the peripheral ADC. So what are the important parameters of an ADC? So suppose if tomorrow you want to buy an ADC, then of course you should always visit the data sheet before going to any purchase. But most common or most generally used or important parameters of an ADC are resolution, non-linearity of the ADC, signal to noise ratio, power dissipation, relative speed and precision. There are of course many more parameters of an ADC, but here I am just limiting myself to this particular list. Now, what is resolution of an ADC? Resolution is one of the most important parameter of an ADC, or even in case of DAC, digital to analog converter. Resolution indicates the number of different, or we can say discrete values which the ADC can generate, but it can generate within a particular voltage range. So we must know what is the voltage range in which the ADC can work, and we must know how many discrete values the ADC can generate within that voltage range. What does that mean? Means, for example, we can look into the mathematical aspect of an ADC. So any signal, okay, can be broken down into some discrete levels, and that is dependent on the number of bits. For example, if we take an ADC of 3 bit, then of course it can generate 2 to the power 3, that is 8 different levels. So here we can see 000 to 111. So these are the 8 different levels in which the ADC can work or it can generate. So all the signals should remain within these 8 levels. Okay, next, suppose we have the voltage reference 5 volt. Like I said before, we must know the voltage reference and the number of discrete levels. So discrete levels comes from the number of bits, and voltage reference we must know, which is provided by the data sheet. Okay, in that case, the voltage resolution of an ADC can be calculated by this equation: voltage reference divided by 2 to the power the number of bits minus 1. So here in our case 2 to the power 3 minus 1. So Vref divided by 7, which is 5 volt divided by 7. So the resolution of 3-bit ADC is 0.714 volts. Okay, so that means each step between 000 to 001 is 0.714, and similarly the next step, okay, again will be of 0.714 and so on. Okay, so this is what resolution means. So it is very obvious that if we increase the number of bits of any ADC, then we can increase the resolution. So higher the number of bits, the higher the resolution of an ADC. Let us take a look about the concept with a signal. So here we have 3 parameters: voltage, the binary equivalent, which we call digital signals, and time. So here we have a sine wave which is between 0 to 5 volt. Okay, and assume we are using a 4-bit system. In that case, you can see here the first sample which is collected is at assume 2.6 volt. So equivalent binary value is 1000. Next, this is at time t0. At time t1, we are taking the second sample, which is somewhere around 3.5 volt, and the equivalent binary value is 1011. Time 2, we are taking the third sample, and it is reaching up to 4.2 volt. So the third sample is 4.2 volt. The binary equivalent is 1101. Similarly, the ADC keeps on taking different samples of the analog signal and keeps on converting it into binary equivalent. So this way, the rate at which the sample is taken is called sampling rate. Okay, so at different time we take different samples, and the voltages of those samples are converted into binary equivalent. So this is the job of an ADC. I hope with this signal most of the things might be getting clear. Now let us take an example and see how to simulate an ADC using Proteus and Arduino. So for that, we will open the Proteus. Here we have the Arduino 328. Okay, here we have the Arduino 328 block. Along with that, we have a potentiometer, and the potentiometer is connected to plus 5 volt, which we can call the voltage reference, and ground. And the middle terminal of the potentiometer is connected to AD0, which is here, okay, which is analog to digital converter 0 of Arduino. So there are 6 ADCs, ADC 0, 1, 2, 3, and you have ADC 5 and 6. So please go through the data sheet to check which are the lines of ADCs. Okay, now here I have used the serial monitor. Okay, so let us try to simulate this signal. For that, we are using a simple program. In the setup, we are initializing serial begin function at a rate of 9600. Then we are using a loop function in which we are initializing the sensor value, which is the variable. Here the data type is int, which is integer, and what it is doing, it is just doing the analog read at A0 or A0, pin number A0, and that value is transferred to the sensor value variable. Then we are converting this sensor value variable to its equivalent voltage by using this function, which is 5 divided by 1023. Why we are getting 1023? Because the ADC in the Arduino 328 is 10 bit. Okay, so 2 to the power 10, that is equal to 1024 minus 1, it will give you 1023. So 5 divided by 1023 into the sensor value that we have obtained after reading the A0 will give us the actual voltage. Then we are using the serial print function to print the sensor value in binary format, as well as we are using the same print function to print the value in the equivalent voltage value, and we are taking a delay of 500 millisecond. If not needed, you can remove this part. Okay, so let us try to simulate this program. So after getting compilation done, we can check the output on the serial monitor. So it is taking bit of time to compile it. Yeah, the compilation is over, and we can see here we are getting the value. Here the binary value of sensor at A0 pin is this binary value, and then the equivalent voltage is 3.10. Let us change the value of potentiometer here. So right now 3.0999 volt is there, so we can change the value, and we can see here at 2.25 volt we are getting a different digital value. So let us check the complete range. So if we bring the voltage to 0, you can see here it is almost 0. You are getting binary value 0. And if we increase the potentiometer to its highest value, okay, so here you can keep an eye on the voltage 1.3. Then we can keep on increasing the value 1.5, 1.9, 3.5 and 4.9995, and you can see here the maximum value is 1111. Okay, so between 0 to 1111. So this is how we simulate an ADC. If you want to simulate an ADC using the template which is provided by other website, which I have discussed in another lecture, in that case you can do like this. So you can take a project and name it ADC_test. Okay, I am for time being making this project on my desktop. Okay, and then new project, next, create a schematic default, do not create PCB layout, next, no firmware project, next, finish. So after this we will be getting this window. Go to place, components from library, just type Arduino. I have shown you in the previous videos how to load and install the third-party library in the Proteus. And then we can use Arduino Uno, which is Arduino Uno here. Okay, I will place it here, and then I will take place, component, libraries. From there I will take resistor. Okay, and from the resistor window I will take a 10k resistor points, okay, 2 watt, and I will take 10k resistor from here. Okay, no, I will take a potentiometer, so I have to change it. Right click, library, and go to potentiometer, resistors, and then take an active potentiometer like this one. Okay, active potentiometer, keep it on the screen. Then after that you can go to place terminal, and then ground, first ground, then after that go to place terminals, power. Here we can put the power, then connect the two terminals here, and then put the value here, string plus 5 volt. Okay, and now this pin should come to the analog read pin A0. Okay, so I will just keep it here, rename it with the name A0. Okay, and then let us go to the A0 pin here, and I will rename it. Okay, here this pin, I will just rename it, right click, and then A0. So that means these two pins are connected together. And for serial monitor, of course, we can put place and then virtual instrument, go to virtual terminal, place it on the schematic. Okay, I will take these two pins and rename it RX. This pin is RX, and here we have another pin which is right click, place label TX. Okay, so now we have TX and RX, and we know that these two pins are the TX and RX. So remember, in the microcontroller board, TX is connected to the RX pin, so TX is connected to the RX, and RX pin is connected to the TX pin. Okay, so right click this one and TX. So we have created our schematic, and for the code you can go to Arduino and generate a binary file. I have already generated the binary file of the code which I have shown you. So I will go to the program and take the binary file. Otherwise, let me show you that part also in case you need it. Okay. I'll go to the program. Here I have kept the program. Wait a second. File Explorer. Object is here. I will take the code. I will show you that part. Okay. So here we have the Arduino file. Okay. And you go to Sketch. First verify or compile it. After compilation, you can go to Sketch and export compiled binary file. Okay, click on that. Once the compiled binary file is generated, then in that case, in the folder, you will be able to see two files which will have an extension of .hex. Okay, so let us check if the compilation is done or not. So it is still compiling. So after the compilation, we will be getting two more files in the folder where we have the .ino file. Okay, just give it a second. Now we can see we got the done compiling message, and we can see here in the folder there are two extra files which are generated with .hex extension. So we will go to our Proteus, go to the standard .hex file, open it, and then OK. Okay, let me show you again. Double click on the third party Arduino. Click here for the program file. Go to the folder where you have the file, and after generating the hex file, click on the standard .hex file, open it, OK, and then run the program. Okay, so here you can see we are getting the same function or same kind of behavior which was generated in the previous file also. So in both cases, you can simulate the Arduino and see the effect of ADC using Arduino. So this was all about reading the Arduino file and the project using Proteus. With this, I would like to end this lecture. If you have any doubts or comments or suggestions, please post them in the YouTube link. And thank you for watching this video. If you have not subscribed the channel, then I would like to request you to please subscribe the channel. Thank you and stay safe.